fairly strong. Good afternoon. For the next to last day of this course in QCD, we have been looking at the infrared aspects of QCD. What happens if either loop momenta or emitted momenta from emitted particles get very soft or small or parallel to their massless emitters. All of that gives rise to divergences. At the same time, that goes together with logarithms. And last time we have been discussing what happens to those divergences. We can normalize. What do we do? Well, we invoke the KLN theorem. In fact, the nice thing is you don't even have to invoke it. You don't have to say, well, I have a right to scratch them out because of the theorem. They just cancel for you, and you can interpret that in the context of the KLN theorem. And the KLN theorem basically says that IR divergences, and with that I mean both really soft and collinear ones, cancel when summing over degenerate states. I wrote a longer version before, but I'll give the short version here. And degenerate states, I mean those degenerate states that hardly differ in energy and are part of the set of final states that belong to the observable that you're looking at. Of course, we looked at one particular one, the total cross-section for E plus E minus to anything. Now, you can't get more inclusive than that. All states are included, all QCD states. So certainly degenerate states are part of the sample. But you could even be a bit more differential. You could think of jets. So when you have, say, a cone definition of a jet, then you can include both emissions and loop directions. Both are infrared or collinear divergent. But because they're both allowed to be part of the jet, they're actually within the jet, the divergences cancel. And the same holds if you 2, 3, 4 jet production. There are lots of other observables in E plus E minus, so-called event shapes, where you don't define the jet, but more you weight the final state with its structure. Thrust is one of them. And there's many others, many observables, and those that obey KLN theorem are called, is also okay, these are infrared safe. And in words, infrared safe really means in practice, if you have a definition of an observable, some jet cross-section or some something else that you like to think of, if you would take one of the parts and it goes into the final state, you split it into a collinear pair. Is the observable still the same? Then it's collinear safe. And if you add from one of the final state parts a very, very low energy gluon, is the observable still infrared safe? Is it still finite? Then that's also a sign of being infrared safe. So if you can, without worrying, if you can have a part that is split into two, and it's still part of the jet, that's okay. Adding a very, very soft gluon, it's still okay. Let me ask you this though. Suppose the gluon is very, very soft and goes out of the jet. Is that then a problem? Just to see what you think. Sorry? Infrared sensitive, or say. Why is it safe? Yeah, so but it's not going in the direction of the jet.
It's not collinear. It's infrared.
Yeah, but is it part of the final state? It looks to be leaving the jet. You see, you should also.
That's fine, but we won't have increase the number of jets.
That's right. Well, the thing is also that's part of the answer, but that's a bit more when it's a bit harder. When you have a very, very soft gluon, really the kind that gives divergence, you can never see that because the jet is defined by a calorimeter, so it measures energy deposit, and it always has a threshold. So there's always gluons that are soft enough you can never detect, and they will be part of your final state. You cannot avoid them being part of the final state because they're just below the detection threshold. So the picture can sometimes be a little bit misleading. That's why I asked you to think about that case too. Now, this is a bit of a general discussion, and I told you that KLM always works for infrared safe observables, except for initial state collinear divergences. And that's what we'll be talking about this first hour. And I'd like to first do it in the context of an actual concrete calculation that we'll just give you the results of, and then later on discuss its interpretation. So let's look at the case of Drell-Yan at next to leading order. We had already seen Drell-Yan at leading order. We had, to remind you, quark anti-quark annihilation to a mu plus mu minus pair, and we had even computed the fact that if you just want to make an off-shell photon, what conversion factor you need for that. So that's a nice simple process. Now let's look at the next leading order correction. There were two kinds, which we now have seen. There were either virtual corrections that you then must compute the interference with the Born for the cross-section. You need just two powers of the coupling extra. So we have, for example, the following diagrams. I'll just make it a final state photon now. I would ignore the muons. So we have one self-energy. We have another self-energy. And we have, of course, our friend, the vertex correction, seen that many times. Are these, in the context of also of renormalized theory, the only contributions at order G squared? It's a bit a tricky question. Those come in a moment. I'm just asking at the virtual level. But you're right, they will be there. The question is, are these the only contributions, these three loop diagrams, I need to take into account in the virtual part of the NLO calculation?
There is one more that photon section.
No, this is a photon. I'm looking for gluon corrections. So that would be a QED correction. I'm looking for QCD corrections. You can, no, that wouldn't be at this order. You cannot have that. Sorry? No, I'm not. Actually, it's a bit of a tricky thing. It's the following three diagrams: counter term, counter term, and counter term. These are these Z-1 terms we've been talking about. Here, this is a theory that we're dealing with a renormalized theory. You have to include them. It's a recipe, right? We have to add those two. So we have 6 diagrams to compute. But now some nice properties happen. First of all, as it turns out, the sum of these three, the sum of the counter terms is 0. As either you can check it from the notes you have, or you can also understand it, and you can also understand it. It's not either or. The reason, I'll just make this remark and you can think about it, why this doesn't, the sum of these three is 0 means that this electromagnetic vertex does not renormalize on the QCD. And that is important because it means that the proton charge is still just E. The proton charge is not a function of the QCD inside the proton. So it does not run with the QCD coupling. So if the counter terms for the electromagnetic coupling here, the sum of all three are 0, there is no change in the electromagnetic coupling here due to QCD effects. These are QCD counter terms. So that's something to think about. Alright, that cuts down the problem in half. Now it turns out that these guys are also 0, these self-energies. And they are 0 because of one of the rules of dimensional regularization, that massless tadpoles are 0. Turns out these are loop integrals without a scale. And they have this rule that we asserted at the end, that's the integral of q squared to the alpha is 0 for all alpha. That's a consistent rule in dimensional regularization, and turns out that these two diagrams are proportional to that integral, so they're 0.
If you take the quark as a small mass, then another term.
No. You must work in a consistent calculational scheme, and the calculational scheme is a massless on-shell quark. If you start making small masses, then they're non-zero, but then the whole calculation changes. So you must work consistently. You can't just add little bits of masses when you want to. Leaving only that one, we've actually, some of you have partially calculated it, so all I will give you is the answer. So you have your 3 massless denominators, 2 Feynman parameters. You can do those integrals, and the result is d sigma q cube r. So the virtual part, v, divided by dq squared equals some Born factor, sigma 0, for making the photon. Then this the electric charge factor for the quark, so 2/3 if it's a up quark, CF over 2 pi, that's a QCD color factor. Some factors that you find in dimensional regularization, minus epsilon over 2, and then the always present Euler gamma functions in dimensional regularization, but written such that they are not dangerous, right? They're 1 plus order epsilon. And then the following expression, minus 8 over epsilon squared plus 6 over epsilon minus 8 plus 2 pi squared over 3 plus order epsilon, all of this times delta 1 minus z, where z is q squared over s hat. So a nice compact formula for the cross-section now. What I've done is I've squared this, or I took the interference of this diagram with the Born, integrated over the phase space. Actually, there was no phase space to be integrated over because there's no extra emission. It's a loop diagram. I integrated over the loop momentum, and out comes this. So let me make a few observations here, along with you. First of all this, you see here this prefactor, that's all dimensional regularization stuff. There's epsilon, epsilon, epsilon. So there was a Dirac prefactor that I'll later abbreviate. But it's just there, and it's not particularly bothersome, except you cannot forget it, because when you expand this in epsilon, you see that you get logarithms, possibly. Also note double pole in epsilon. And you can tell me already why there was a double pole. Why is this double pole there? That's exactly right. So this is indeed the overlap of a soft and a collinear divergence. Of course, there are also the less severe poles, the singular pole that could be either an IR or a collinear divergence. And then there's finite stuff, not even that much, 2 terms. And then there is a delta 1 minus z. That is there because, well, z must be 1, right? There is no extra radiation coming from the initial quark and antiquark, so s hat must be equal to q squared, so z must be equal to 1. So we've understood this. Of course, an overall factor of alpha s has been dropped. That you should think along. That's there, but I just didn't write it because it's order g squared. Okay. So this is a sign that trouble is ahead if we didn't know any better. But now that we know about the KLN theorem, we think, this is bad, but no, we shouldn't worry. We still have the real emissions to compute. And according to KLN, that should fix it. So we expect poles to cancel when adding the real contribution. So that means I'll just draw it very briefly. Emission from here plus the emission from there. It's only two diagrams. Those we must, the sum we must square, and now integrate over the phase space of this extra gluon. We had done it in the approximation already. We had seen the 1 over epsilon squared appear there. So we're not too worried. And well, it's a bit of work. It's in the notes if you wish to follow it. I'll just give you the result again. So d sigma 1 q cube r. Now the real contributions, they are also real because I take an absolute value squared of this, and it's guaranteed to be positive. The virtuals are an interference term with the Born, so they're not always positive. They don't have to be. So in general, that's maybe a good lesson to NLO is leading order is guaranteed to be positive. That's really an absolute value squared. Beyond that, is not always positive. You can get negative cross sections. It's usually a sign that your perturbation theory is going bad, but mathematically it can happen. Anyway, here is our result. I have a prefactor, and that's this whole prefactor here. And we call this C epsilon. It comes up again, so I don't want to write it all again. And then we have the following result. 4 over epsilon. I'll just write the result first, and then let's inspect it. There we are. Not too long again, less than a line. So we have some remarks to make again. The first one is now z dependent, no longer a delta function, no longer this distribution, this delta function, but we have a function of z. And that is not so surprising because we can now have s hat larger than q squared, then radiating off extra energy, and then finally producing q squared. So z doesn't have to be equal to 1. So that's okay. But the real problem is only a single pole. That's the only pole I see here, right? Together with the function of z. So here we have to think a little bit what to do, and because KLN holds, I mean, we shouldn't immediately throw that overboard. Now, if you inspect this function of z, there is something to see. First of all, and the real interesting limit is z is 1. Right, that's where the virtual corrections sit. So let's inspect this in the neighborhood of z is 1. This factor is very innocuous. The whole second term here is quite innocuous. Right, this is power plus 1 with epsilon, this is fine. Here's the one that's tricky. Right, this is 1 over 1 minus z to the power minus 1 plus epsilon. There's a divergence here as z is 1. And we like to bring that out in such a way that we can cancel it against that. So cancellation will happen using a little mathematical trick. Math trick. It's not even a trick. It's the definition of a new kind of function, which we'll do now. Brush, brush, brush. We have another, okay. And when we do this trick, we have to remember that what we have here are partonic cross-sections. They're not yet the hadronic cross-section. For that, we still have to multiply these results, or integrate these results with PDFs, smooth functions of z. So the mathematical trick is, so consider indeed this particular factor 1 minus z in the power of minus 1 plus epsilon. Really quite divergent here, e equals 1. What we can do now is extract the divergence in the following way. Let's consider this expression underneath an integral with some smooth function f of z. 1 over 1 minus z, 1 minus epsilon. And this is some smooth function. Take the PDFs. Right. Now I'm going to write this as f of 1 times the integral of z, 1 over 1 minus z in the power 1 minus epsilon, from 0 to 1, plus the integral from 0 to dz, f of z minus f of 1 divided by 1 minus z, 1 minus epsilon. I add and subtract to the same term. So first of all, I can compute this now. This is minus 1 over epsilon. And here I've written it in such a way that you see now that z goes to 1 behavior is modified. It's tempered. We have now a difference upstairs as well, rather than only downstairs. So the following step is only a few more steps. As I write f1 as the integral over z, fz of delta 1 minus z. This is f of 1 here. And this expression I write in terms of new types of distributions, functions that let me do it this way, times 1 over 1 minus z plus the epsilon times the logarithm 1 minus z, 1 minus z plus, etc. So I've defined here something new. These are called plus distributions. They're not functions, they only are things which make sense once you put them underneath an integral with a smooth function, a distribution. And you see here what the plus means. The plus just means when I integrate this with a smooth function, take the smooth function minus the smooth function at 1 and divide by this thing. It only says to subtract the function at 1 in the numerator. And the same thing here, if I expand this epsilon, I get a log of 1 minus z. And it just says multiply this expression with f of z minus f of 1, and so forth. And it continues. So these are plus distributions occur all over QCD, so they're very useful to introduce. So we have actually a distribution identity. I can now write the summary minus 1 plus epsilon is delta 1 minus z plus 1 minus z plus minus epsilon 1 over 1 minus z, log 1 minus z plus 1 half epsilon squared log squared 1 minus z 1 minus z plus, etc. So this is a useful identity. I strip now the smooth test function off. So I can expand this factor in a series of distributions. And now you see that the constant cancellation of the double poles at least happens. So we can substitute that here. Right, the first term is just the delta of 1 minus z, sets this equal to 1, and double pole cancels. Right, so substitute in here this long expression. Just look at the leading term. I get here x to 1 over epsilon delta 1 minus z. So now I do get a double pole, and with a delta 1 minus z, and the coefficient is precisely such that it cancels this one. Okay, so that's how, and there will be single poles as well. Is this clear? It's just mechanics now. Once you use this trick, matter of substituting and gathering terms together. Okay, so now it's interesting to write the combined result. Let me do that here. I have more space. So total result is delta sigma 1 virtual plus real the q squared for the QQ bar channel is, here's my C epsilon again, that long prefactor, and then the following expression, 4 over epsilon 1 plus z squared 1 over 1 minus z plus 3 halves delta of 1 minus z plus 4 1 plus z squared log 1 minus z 1 minus z plus a few more finite terms, just 2 or 3 more, not too much, and that's it. And these extra finite terms are in the notes that you have. Okay, so KLN has worked at least to some extent. The double poles have cancelled, but there is a single pole left over. Now this thing here, between the coefficient of the single pole, can also be written as, is usually called the quark-to-quark Altorelli-Parisi splitting function. So maybe you've heard of that, and there it is. Now, we can give it a name, but it doesn't solve the problem. Right? So what do we do now with this remaining 1 over epsilon divergence? So how to get rid of the question is how to get rid of 1 over epsilon times p QQ pole. And the answer is renormalization, but not of the fields and the parameters in the Lagrangian, but we normalize the Parton distribution functions that describe the probability of getting a quark out of a proton, etc. So that's what you should do, and we'll do it also in a second. So we can renormalize that. That's renormalize. That is not something we've done before, but if we do it now, I'll tell you that it works. And there's a number of parallels still with UV renormalization. Let me first give you a physical argument, though, why this would be a sensible thing to do.
What if we were to start with an E plus E minus collision?
Then you wouldn't have this. If an E plus E minus collision, the answer would be finite right at the beginning, right after combining. It's because we have initial state quarks that we have this problem. Or initial partons, any parton would have the problem. Or it's brilliant, we have a quark anti-quark annihilation. If you had E plus E minus, all the poles would cancel with KLN. So why would this make sense? Now, the nature of this divergence really is a collinear divergence. So suppose here we have the hard scattering, HS, and here is our quark coming in, and then here the photon coming out, the anti-quark. The singularity that this corresponds to is a collinear one. So imagine a gluon radiating very, very collinearly. And the more collinear it is, it's almost collinear, the more collinear is it, the further up the line it occurs. And then this bit of line between the splitting vertex and the hard interaction has a very low virtuality. Right, this line is almost on shell. But if you have very low virtuality, you can live a long time. Very large virtuality is short-lived. Small virtuality is a long-lived. So really, the real extreme case is this splitting will occur long before the hard scattering, and then propagate all the way into here. Now, viewed from this way, this is much more a property of the proton than of the hard scattering. So it's best to combine this with the proton wave function, the PDF, than with the hard scattering. So this is the proton, the realm of the proton, this is the realm of the hard scattering.
There's some, I mean, you gave a qualitative argument, but is there some criterion, mathematical criterion that's used?
I'll give it now, but I'll tell you how it looks. So I just gave you the argument, now I'll give you the formula. Okay. So you were right on time with your question. So here it is. So and it is a bit like, recall the case of renormalization where we had the bare coupling is the renormalized coupling times ZE of the renormalized coupling and 1 over epsilon inside. That was what we did in UV renormalization. Now we do the following. The formula is a little bit more involved because we're dealing with functions rather than with numbers. But here it is. So the bare PDF, the one that corresponds to the parton model, parton I, the proton, I subtract from that, so I write this, as dz from 0 to 1, dy from 0 to 1, delta psi minus zy. That is a way of writing a convolution as I did in tutorial this morning, times phi of IP of y and mu. And then what is essentially equivalent to a z factor, but for convention I call it phi inverse, but it is the equivalent of the z factor, except it's now a z function, 1 over epsilon, z and mu. That's it. So this is like the bare function is the renormalized function times the z factor containing the divergence. We also see, just like in this case, a mu has appeared, right, that it was not there on the bare function. Often, this mu, to distinguish it from this one, people then call this the renormalization scale, and this the factorization scale. You can choose them to be the same, you don't have to choose them the same. I will often choose them the same here to avoid needless clutter, but it's just maybe to be aware that this mu comes from a different type of factorization. Then here you factor off the UV modes, here you factor off the collinear modes. And it's a different mu. In principle, but indeed most often it's chosen the same. So remember also what you do with this. You eventually make z minus 1 terms with the z factor, count the terms that cancel the divergence from the loop diagrams. So what do you do with this thing? This will give you extra 1 over epsilon terms that will cancel the 1 over epsilon there. Same story. So this will be in practice phi IP of psi and mu f minus the integral from z over z from psi to 1 phi I over p psi over z mu f times, actually it's alpha s over 2 pi times exactly this splitting function that I wrote there. This is times exactly this splitting function. So here you see really a second contribution coming in, and there's a 1 over epsilon in front here. This is let me make it explicit, 1 over epsilon. Well, I write it explicit, I admit it's not very visible, but there's a 1 over epsilon there.
So except otherwise it doesn't come in, that will cannot absorb. And you can absorb that in terms of the
That's what you have. Or the other way around, you write the bare function as the renormalized one times new divergences that will then cancel the ones that the diagrammatic calculation gave you.
But for T plus and E mass solution, we do not.
This not necessary. No. It's only for initial state collinear divergences dealing with the incoming proton. So this would be epsilon x to 1 of epsilon sits. So this cancels. So we can make some remark. Note. Let me make the remarks in the center board, erasing our identity of plus distributions. So remarks. As in UV renormalization, the factorization, that's what you call this, introduces a new 1 over epsilon that cancels the 1 here. That's one remark. I said that already. Now the second important remark is these 1 over epsilon terms are universal. So it means process independent. It will work for any other reaction. This is important because if I renormalize the proton in such a way that I get an x to 1 of epsilon, then okay, I can cancel my problem there. But if for some other reaction, TT bar production or 5 jet production or W plus 10 jet production, every time it's a different factor, I don't have predictive. I can't renormalize the proton with constantly another divergence. Thankfully, these divergences are universal. It's always the same function that you find, and it's been tested many, many times, of course, to higher orders as well. So thankfully, these are universal divergences, just like in the UV case. So a third remark, again by analogy, we had a byproduct of this renormalization. The byproduct was the beta function equation. Right, just by demanding that this product is independent of mu, we got an evolution equation for the coupling that told us the coupling either goes down or goes up as a function of mu, depending on the theory. So get an evolution equation for, now not for the renormalized coupling, but what you get the evolution equation for, you think?
PDFs.
For now the renormalized, the mu dependent PDFs. Right. For the phi I and p psi and mu f. And we can actually derive that equation together. So you can sort of see what happens now. I have this equation that renormalizes the PDFs. And then I act with mu dd mu, mu f dd mu f. 0 on the left hand side. And I get something, well, what do I get on the right hand side? I get here the derivative of this is equal to the derivative of this. Now where does mu dependence come from? Actually it comes in from here you pick up a mu to the epsilon that kills this epsilon, and you get the following consistent evolution. So the result, mu f dd mu f on I of p psi mu f is dz over z from psi to 1, p of z and alpha s of mu f times phi of I of p of psi over z mu f. So a change in phi gives you this splitting function times phi itself, but a slightly different x. So it's psi over z rather than xi itself. I'll give you an intuitive picture of that equation. I should also modify it first. I did this. This is for parton of type I, and in this evolution, actually, parton flavors can mix. You can have a gluon split into a U bar, etc. So these things can mix. So you have a bit of a matrix equation here. Sum over J, I, J, and here's J. It's an 11 by 11 integral differential equation. And this is known as the Altorelli-Parisi equation, or perhaps even more common, the Dirac equation. Who knows what that stands for? Sorry? I didn't get the... okay. So AP is again Altorelli-Parisi. This is Dobzhitzer, Gribov, Lipatov. These are 3 Russians. But Dirac is... sounds like a Dutch name perhaps, but it's not. So this is a very famous equation, right? So we'll certainly say a bit more about it. So it describes the evolution of PDFs. It says that if you vary the scale of a PDF, renormalize PDF a little bit, how do you determine that? Well, you integrate phi with the splitting function. In this prescribed, it's an integral differential equation. It looks quite formidable. It's actually not that hard to treat. But it tells you how, if you have a function of psi at a certain scale, from 0 to 1, could have some shape. As you increase the scale, that function could change shape. So if you have a function at a low scale that behaves like this, from 0 to 1, at a higher scale, the evolution starts behaving like this, even higher scale like this. So this is what the function tells you. How does the shape of the function evolve with the scale? So the function as a whole is non-perturbative, but its changes in mu are perturbative. You can compute when it changes in mu what the change is, and that is a perturbative change. So you can determine the PDFs by comparing the theory at low scale and evolve or compute them then to a high scale, or vice versa. That's both possible. It's a linear equation. It can evolve up and down. And there are groups. So this is done, groups that do this. I'll have a few slides in the last lecture on this, that do this. I've mentioned them in the first lecture, 2NN PDF group, the CTEC 10 group, and a few others. Now, so this is the equation that follows from the factorization of initial state collinear divergences into the PDFs.
For E plus E minus solution, you don't have the renormalized step.
There are no PDFs.
But they don't have any evolution.
Sorry?
They don't have any evolution.
There's no PDFs even. It's E plus E minus. There are no initial state partons. So you don't have to do this. Right? It is not there. Right? So if they're not there, they don't have an evolution either. Now, if you would detect a particular meson, you get sort of a final state equivalence of these sort of fragmentation functions. But I won't discuss that in these lectures. So let me just devote a few remarks to solving the Dirac equation. And let me first give you a little picture of it. So suppose at some scale, here is the proton, and the photon detects a particular quark here. This is a photon probe. But it can, well actually let me draw it like this. Comes out here and it hits there. Now if you would go increase your mu f, you increase like this, then then turns out that what could have happened is that a splitting of the quark, which is first not visible, part of the proton, is now visible because you look with a higher resolution. But you look with a larger scale, it means a better resolution. And what was first not visible, the splitting inside, is now visible. So we need an increase in scale is proportional to a splitting times the PDF, where the particle coming out has a slightly larger momentum, which it then radiates off, and then is being hit again with z exactly where the original one was hit. So that's the content of this equation. Okay. So one way to solve it is, let's ignore the particle flavors, ignore I and j. So one flavor only, just for ease, is to take the melon moment. That would be take the following integral on the left and the right hand side. And then the equation becomes mu f d mu f on phi of n mu f is p of n mu f phi of n mu f. A nice simple product. See really the use of the melon transform. This kind of forbidding form becomes a simple product in melon space, in moment space. This you can solve, I presume. I'll write the solution. Solution is phi of n, sorry, just regular phi of n mu f equals phi of n and mu 0 times the exponent of mu 0 d mu prime over mu prime p of n alpha s of mu prime. It's mu 0. So you can just, it's a very simple first order differential equation now, and it's an exponent solution because you have to divide d phi over phi, that's a d of the log of phi, etc. So you see here that when you solve the algebraic Puise equation, you have an exponential, you have resummation of of a series in alpha s. Now this splitting function is known to third order. So the first order diagram is known. That's the one more or less we sketched, this thing. That is one diagram only. The second one is not a much longer calculation. The third one took 3 people, lots of computer algebra, 5-6 years, 10,000 diagrams, and it's absolutely necessary for doing second order perturbation theory at the LHC. And the importance of it is that this is a universal function. So this is not just true for one process. This was necessary to do any process at the LHC to that order. So this is a key central component to compute this to third order. It was done by my colleagues at NICAF, but it was really known by others also as the calculation of the century. That was of the last century. That was really very well done. And we also know now how to go back, right? In the tutorial I showed you, once you have it, how you go back to X space with this inverse melon transform. I won't write that down. So Going to transform space is many times the case in physics. Things are easier to solve, and then you just have to go back later. And misery is somewhat conserved, but sometimes there is a bit of a misery lessening when you do these things. So we have now the full story for a fixed order calculation. We have seen that if you do a partonic cross-section calculation, a lot of poles cancel, UV from renormalization, the infrared ones with KLN. If you have initial state partons, you will have leftover 1 of epsilons from collinear splittings. And now we know how to get rid of those two through this factorization procedure where you renormalize the PDFs, and those new 1 of epsilons cancels the ones you still had to make a finite result. As a byproduct, these PDFs, the ones you really should be using in a calculation, depend now on 2 scales besides this psi, this momentum fraction, also on this factorization scale, which is again a feature, not a bug. You can use it to evolve these functions to higher scales. And that's now a very nice whole package where you can start doing calculations, and it becomes quite almost automatic. But I think this is the general structure. Now, for other processes at higher orders, of course, the calculational details become more tricky, the phase space integrals, the loop integrals, but the basic story is always the same. After doing all that, defining an infrared safe observable, there will be only these initial state 1 of epsilons left, and now we know how to get rid of them. Maybe it's good to say a few words now about the present status of just a few words. I'll say a bit more on the last day on fixed order calculations. Before doing that, actually, I should make the remark that this Mellon technique is certainly a nice way of solving the Altorelli-Parisi equations. Analytically, it's great, right? It's beautifully simple. The only trouble is you have to go back to X-space to this inverse transform. That is often a bit more tricky. So these professional groups often use slightly different methods. They don't go to Mellon space. They solve the equation as it stands using very clever techniques, interpolation, and that's just often it's just as accurate. There is no loss of accuracy. The key for these methods, whatever the method is used, must be fast, because you must be very quickly when you do fits to data. You must be able to very quickly solve this at yet another scale. You shouldn't have to wait an hour for to go 2 GeV higher. It must go very fast. So what is the present status? Well, roughly, if you look at leading order calculations, that sounds, well, isn't that trivial? Well, it was trivial for Drell-Yan, right? You had there, but you could also have, say, 15 jet production, and but you can have lots of gluons, say, right? So 15 of them, no loops, but the number of tree diagrams is gigantic. That's in the hundreds of millions. Right? So tree level is not easy always. Nevertheless, the status, it's automated. So there are now codes that if you demand a certain final state, the program will produce it for you. If you want also the diagrams, although it's not always smart if you have that many. So automated, so for 2 to n processes. And such codes will produce the cross-section. It will make histograms in any distribution that you want. So that really everything, the ideal tool for the experimenter. The theorist is now useless. It's all, the theorist has been sublimated into a code. And the experimenter can use it and act like a theorist. And actually better than that, because it can do many more jets and many more complicated diagrams. So on codes such as AlpGen, you have MadGraph, There's a number of others for specific processes. There's not only one. Different people have made different ones. One of these codes, at least, relies on the fact that you don't. It's a bit of a different approach. Just mention it in words. Not to write all the diagrams. As I said, it can really get out of hand. But to use a sort of recursion. It's a tree-level structure, and you can set up recursion for going back along the tree to the beginning, or start with two partons and then evolve in a recursive sense. That is called, that's particularly what Alpgen uses. MATLAB uses diagrams. So now next to leading order, so then you have one loop and also one extra radiation. This is now also fully automated. This is really quite a remarkable story. So just 10 years ago, there was a lot of handiwork necessary. And this involves, for example, not just triangle diagrams, but you could have lots of extra partons. So this is a one loop graph with lots of propagators in. All of that is automated. So again, you run the code, choose the option NLO, and you will get NLO quality calculations spit out as histograms or as curves. And this is codes like PowerHack Box, and particularly AMC at NLO. So this is NLO, and there's even Monte Carlo that you can add to it. I will not be talking about Monte Carlo in these lectures. But so, and there's a few others. So this NLO fully automation has been possible because of a new insight. Well, actually, it was not a new insight. Finally, making it work. This so-called NLO revolution. That's the people always thought it was. Every time you add an extra final parton, it gets infinitely harder. And then it turned out a trick was found such that it doesn't get harder at all. And suddenly the whole thing broke into pieces and became fully automated. Well, a fantastic achievement. At NLO, a few calculations exist. No automation. For example, we have TT bar. I told you about that already. We have dijets and the single jet inclusive. Those are for 2-to-2 processes. There's already a long time 2-to-1 processes, but I'll reserve those for the next item, which is the NQ below. Then it becomes a really rarefied heights, rarefied air. So an NQ below, third order perturbation theory. There we only have two observables. The structure function, the DIS, is known to third order perturbation theory. So that's essentially off-shell photon, off-shell photon hitting a quark, and then think this, 3-loop diagrams. And also, and that's really quite amazing, Higgs production. So you have gluons making a I keep on drawing time the wrong way. Gluons making a Higgs, and then having 1, 2, 3 loops, and also the radiation that goes with it. So that exists at NQ below. Beyond that, there was nothing. So these are fantastic achievements and great tools to compare data with theory. So that's give you, I hope, a bit of a sense of QCD at fixed order in the context of the LHC, both at the level of calculating hard scattering cross sections, but also what you do with the PDFs that you then still must multiply that with for the full hadronic result. So after the break, then we have, I'll start going further, but immediately I'll jump to all orders. Any questions? That's a good point. So indeed, the rule is, I haven't explained what the rule is, if you have an enter the ILO calculation requires an I plus 1 loop PDF or splitting function I plus 1 loop beta function. So if you do NNLO, you need 3 loop splitting functions and 3 loop beta functions, both are known. For NQBLO, where we need a 4 loop splitting function, we don't know that. And the 4 loop beta function, that is known. We even by now know almost a 5 loop beta function, so we're okay there. The one thing we can say is that if we look at the behavior of these splitting functions as you go up in order, they become ever less numerically important. So formally they're necessary, but we expect, based on evidence of lower orders, that numerically they will hardly make a difference. But for full consistent calculation, we should have the 4 loop beta splitting function, and people are working on it. With new techniques, new methods using Hopf algebras and various other mathematical techniques, these things are coming into view. There's a whole fantastically inventive team of people that work on these things. Okay, then let's have some tea. Is that a good idea?
What was the technique used for making those multiple leg NLO calculations simple? Those
Turned out,
recursive.
yeah. The trouble was this is the need of the vector. You don't have a thing on it. It's not simple. So the problem looked at I order to get pentagons, hexagon, heptagon diagrams. It turns out beyond boxes, beyond box diagrams, you can write everything as a sum of boxes, triangles, bubbles, and templars. You never have to go beyond the box. You can write any diagram as a decomposition of that. Now, that's still not enough.
Wait, so this is the plus 3 number?
No, that's something else. So even a diagram with 32 blue ones coming out, God knows what it is in Latin, it's a Hesselhoff diagram, whatever, but you can still write a sum of box, triangle. That's one thing, and now the other thing is that they found very clever ways of getting at coefficients. People have now a complete basis of all box, triangle, and bubble integrals. And if you know that all you have to do is find coefficients, and there's very efficient ways of getting these now using so-called cutting techniques, finding imaginary parts in a sort of recursive cleanup procedure. And it can be almost automatized. So that was really the key. And the reason it's a box and not a pentagon is because we live in 4 dimensions. It turns out related to each other. If we live in 5 dimensions, we would be that was really big. Well, we certainly have to be dealing with pentagons.
Please, yeah. She's out there.
I'm okay, but maybe I'll sleep a bit.